different types of functions that we're dealing with is we're not just looking at a bunch of functions because, well, gosh, we got to find something to cover the whole semester. So we'll just include every kind of function we can think of. The reasons these functions are included is because depending on what you're doing, depending on what kind of a job you land, these functions can actually represent some aspect of the company, the job, okay, the income, something or other related to what's going on. Okay? So the whole point of this isn't to just get you a whole bunch of different functions to look at and go on from there. It's to prepare you for different things that can happen. The whole point of equations and functions, any idea why they made up these different equations anyway? Was it to kill off the dinosaurs? Here comes a stegosaurus, we'll throw a cubic at him. And boom! It's the end of the stegosaurus. Where did these things come from originally anyway? They came from trying to describe different things that occur. For example, back in old and Middle Ages, every king hired a group of mathematicians. And the reason that they hired mathematicians is because when they would go out or when they were under attack, one of the things that they had was a cannon. When you shoot that cannon, the objective is to do what? Hit whatever you're aiming at, right? Whether it be a wall or, a castle or who knows what, you want to hit them. If the angle of that cannon isn't right, if the amount of powder in the cannon isn't right, that shot could go way over like this, and the people are all laughing at you for being a bunch of idiots. Or it can fall far short and hit in front, and once again they're shaking their head saying this is really going to be an easy day. Okay? So they hired mathematicians to go out and to compute what the trajectory would be with different amounts of powder in different angles. Now what you then have is a situation where you can vary the amount of powder and you can vary the angle that the cannon is set at. So you needed equations that you could put two different variables in. Powder and angle. And then from that, out would come the range, the distance that the trajectory, the cannonball, was going to go. And you can't keep repeating the experiment while you're out on the battlefield. You've got to have a quick way to compute this stuff. Hey, they're out there about 200 yards. How much powder? What angle? Ta-da! That's where the equations come from. There are lots of things that folks were trying to describe and trying to understand. Even things like planetary motion. Okay? One of the things that's kind of interesting, or I think it's kind of cool, is if you're sitting here on planet Earth, and you're looking out and watching a planet out here. One of the ways you can tell where the planet is compared to the stars around it. Well, as you watch that planet and you track its pattern night after night after night over a period of a couple of weeks, the planet will progress along, and over a period of weeks you can see it moving through the sky. And then it'll do something really weird. It'll loop around and go backwards. And then it'll turn around and continue on its original path. That's called retrograde motion. Well, that's kind of weird. Well, back then they didn't have cool things like the Hubble telescope and all the kind of stuff we've got going now. And they had to figure out how is it that a planet can be moving along and suddenly turn around, loop, and then continue the way it was. Kind of strange, isn't it? And they had to work that out mathematically. And once they got a set of equations that would really describe what was going on, but make sense, because they knew the planets can't be going around like this. It just didn't make any sense. Once they found something to describe what was going on, like, oh wow, maybe the Earth isn't the center of the universe. That was a big one. There were astronomers who were thrown in jail for saying that. Because that just violated everything that they believed at that point in time. The Earth's got to be the center. Well, maybe not so much. Okay. So, these equations that we mess around with in a variety of cases came from actual applications that have been around for a long time. And over a period of time, it's just different equations building on. Yes, sir?
Isn't the universe always expanding?
It is.
So what if back in their time it was, now it's not?
Please?
Like, what if it was back in their time when it wasn't as expanded as it is today?
Okay. Yeah, it was smaller than it is now. And were you going beyond that, or just?
Like, so
I want to make sure I'm not missing something here for you.
So when they discovered it, what if it was like the center of the universe then, and then today it's proven it?
Oh, okay. That's only been a couple hundred years.
Oh.
So, yeah. And when you're talking about astronomy and stuff, a couple hundred years is no time at all. Yeah. Here's an intriguing one. I've thrown this one to my kids. The universe is expanding, right? What's it expanding into? What's beyond space? What's beyond the universe? Because the universe is getting bigger, but what's beyond the universe? Please? So how far does the universe go? It starts to get kind of weird when you think about it. Yeah, there's not just a boundary. There's not a sign that says universe stops here. That's kind of amazing, isn't it? It keeps expanding, but what's out there where it hasn't been yet? Kind of some. Anyway, don't mean to spend the whole class on that. That's astronomy. You can have that with Dr. Gallagher. He does a nice job with it. But I want you to realize that these equations aren't just things that people have thought up to torment you and make another section in a math book and create yet another set of homework. The stuff actually has applications. Okay? And right now, you're just picking up on, okay, here's how we do this, here's how we do that, here's how we do the next thing. And then later on is where you're going to get the applications, depending on what direction you're heading. Okay? Okay, so what are we going to do here? We're going to learn to, first off, identify what a rational function is. That's pretty easy. And figure out its domain. The domain is the x values it's allowed to use. You can't always use any value of x that you just pick out of the air. Some of them will cause the function to blow up. We're going to identify and interpret asymptotes. What are those? If you have a graph with some vertical asymptotes, like one here and one here, can the graph cross over those dotted lines? They're kind of like fences, aren't they? And they fence the graph in to keep it from going some places and allow it to go other places. Vertical asymptotes, as we'll talk about, you're never allowed to cross. It's kind of like electrified barbed wire fence. You really don't want to mess with it. You just stay away from it. Okay? We'll also get horizontal asymptotes. Talk about those. Okay? where I'll talk about how do you graph these functions using transformations. And gosh, you can actually graph these things by hand. I thought I needed a calculator or a computer or something. Nah, they've been graphing these long before there were calculators and computers. Okay, first off, what is a rational function? A rational function is something that comes in the form of a fraction. So an example of it would be something like k of x equals 4x squared minus 9x plus 6 divided by, and we could have something like 5x to the 7th plus 6x squared minus 11. In the numerator, the 4x squared minus 9x plus 6 is a polynomial, isn't it? In the denominator, the 5x to the 7th plus 6x squared minus 11 is a polynomial. They're each a polynomial. Different parts of the fraction that all together is called a rational function. It's kind of strange to think about the universe, isn't it? Okay, the domain is all the values of x except those that put 0 in the denominator. For example, let's say we have something like g of x is equal to, let's say x minus 3 over x squared plus 5x plus 4. Now the first thing to ask yourself is, hey, you see that x squared plus 5x plus 4? Will it factor? Yeah. What this really can be rewritten as is x minus 3 over x plus 4 times x plus 1. With it factored, are there some values of x that are our problem? Well, let's see. A problem would mean places where you get a 0 in the denominator. Are there places where you can land a 0 in the denominator? Well, what if x equals negative 4? You see it? That'll give you a 0, won't it? If x equals a negative 1, oh yeah, that's a problem. That'll give you a 0. And when you have a 0 in the denominator of a fraction with 0 in the denominator is undefined. Make sense? So these values of x produce what are called vertical asymptotes. On a graph, we would come to negative 1, and do a couple of dotted lines like that. Those would represent the electrified barbed wire that the graph is not allowed to cross. However, graphs will often get really close to them. Never touch them, but get really close. Like that. Make sense? So these asymptotes are useful in giving you some idea about how the graph is going to behave and what the graph is not going to do. The graph is not going to ever take on a value when x is negative 1. It's not going to ever take on a value when x is negative 4. Hey, let's take a look at these. Is this first function a rational function? Is that a rational function? It is, because you have a polynomial. 2x minus 1 is a polynomial. X squared plus 1 is a polynomial. So you have a polynomial over a polynomial. So yes, it is a rational function. And state the domain. Now, when you're asked to locate the domain, I always kind of think about it the other way around and ask myself, okay, so where could I break this thing? Where is it that x squared plus 1 equals 0. Because if I can get the denominator equal to 0, I broke it. And that's not part of the domain. Okay, so the question is, what number can you put in for x to get that to 0 out? -1? Let's try it. It ain't going to work, is it? Yeah. Please? Okay, the domain is any real number. Because if we even put in -1, it's going to be the -1 squared. And -1 squared is what? It's positive. Yeah. So in this case, the domain is going to be all reals. So x is an element of, and then the r with 2 backbones means real numbers. X is any real number you want it to be. The thing that causes this to 0 out is I, the imaginary number, where I is equal to the square root of -1. Oh yeah, we did that a while back, didn't we? Oh man, that's going to be on this test Friday too. The stuff with the complex numbers. Uh-oh. This one. Is that a rational function? And the answer is nope. Because this can be written as 1 over x to the 1/2 power. Writing it like that, polynomials are functions where the exponents are always integer valued. The 1/2, is that an integer? Nope. So it's not a rational function. Nope. The domain on this would be, well, is there any place that'll break it? Bless you. Is there anything here that'll cause a problem? Negative numbers are a problem. Square root of a negative number puts you into the complex. So the negatives we can't use. What else can't we use? 0. So for this, x has to be greater than 0, and x is an element of the real numbers. So the domain, all real numbers greater than 0. Third one, rational function or not? Yeah. Okay, so this is a rational function. Domain. Ooh, let's see. Can we factor this denominator? Is that factor? Yeah. So x is an element of the reals. And x cannot equal, is it 2 and 1? Or -2 and -1? 2 and 1. Well, if you can factor it out, you've got some points where the domain is undefined. Now, remember, you can also draw this. The domain is sometimes kind of hard to describe. Here's 1, there's 2. I'm going to put a dot around it, an open dot. Okay, and it goes like that, it goes like that, and it goes like that. Another way to define this is from -infinity to 1, along with 1 to 2, along with 2 to infinity. So it can be set up like that. Does that make sense to everybody? So there are a couple ways to note it. Okay, so they've cruised through here, and they've come up with, whoa, look at here. Here's our -1, 1 to 2, and 2 to infinity. So that's all good. All right. let's talk about these vertical asymptotes. The vertical asymptotes are the places like what we were just talking about. Here, x cannot equal 1 and it can't equal 2. So for that particular function, you would have vertical asymptotes at x equals 1 and x equals 2. When you're concerned about vertical asymptotes, it's always going to be where the denominator is 0. So you just take whatever's in the denominator, set it equal to 0, and solve. And that'll give you the vertical asymptotes. Okay. With the vertical asymptote, the graph is always going to curve. It'll get close to it, but it'll never touch it. On this particular graph that's provided, notice how the graph also flattens around the x-axis. That's a horizontal asymptote. Okay, we'll need to talk about those too. But for right now, I wanted to make sure that the vertical asymptotes make sense. Are you okay with those? Okay, so we got our vertical asymptotes taken care of. Now, horizontal asymptotes. How do you get horizontal asymptotes? Horizontal asymptotes come from one of two things. First off, you can have something like y equals, let's say 3x squared over x squared minus 7. In this case, yes, sir. You okay? Okay, in this case, we have the highest power of x in the numerator is x squared. The highest power of x in the denominator is x squared. If there is a tie, you take the leading coefficients and your horizontal asymptote will be at y equals whatever that fraction is that's formed by those leading coefficients. In this case, it would be y equals 3. Now, over here you have one where it's x squared over x squared plus 1. The leading coefficients there are both 1, aren't they? So for that particular function, you would have a horizontal asymptote at y equals 1. Okay, so that's this dotted line that they show here. And the function comes up and approaches closer and closer to that y equals 1. In the example that I gave in the upper right-hand corner, the function would draw closer and closer to y equals 3. Now, here comes something that's different than what you heard about vertical asymptotes. Okay? Be sure you catch this. The graph can cross a horizontal asymptote. For example, you can get a graph with a horizontal asymptote. Okay, and the graph is drawing horizontal, comes away, comes up, and it levels back in. It's legal to cross a horizontal asymptote, not a vertical one. Okay? Does that make sense to everybody? Right. Yeah, it's just the vertical that you can. And remember why with the vertical. It's because with the vertical, that's where the denominator is 0. It can't cross because if you get a 0 in the denominator, the thing is undefined. Okay? So for it to cross a vertical asymptote, the function would have to be undefined. Well, if it's undefined, does it even exist there? No. Are you worried about Bigfoot wrecking your car out there? Go out every 10 minutes and check it, right? Not too worried because does Bigfoot really exist? Okay, maybe we better not even go into whether Bigfoot exists or not. We'll leave that one alone. Okay. Okay. The line y equals b is a horizontal asymptote if you have a situation where as x goes to infinity, okay, you get a number. You're going to get a number in one of two places or one of two cases. The cases where you get a horizontal asymptote are things like y equals 7x to the fourth plus 8x over, let's say 15x to the fourth minus 9x cubed plus 21. Now there can be all kinds of stuff going on here, but what you want to do is look at the highest power of x. It's a tie. So to get your asymptote, it's going to be at y equals, and you just pull the leading coefficients off, 7 over 15. There's one place. Now, there's another place where you can get a y or a horizontal asymptote. And that place is if whatever's going in the numerator, 3x squared plus 8x minus 11, and in the denominator, let's say it was something like 4x to the fifth plus 17x cubed plus 12x squared plus 9. Here comes the second place where horizontal asymptotes exist. If the degree of the numerator is smaller than the degree of the denominator. So here you have a 2 and a 5. What you'll get there is a horizontal asymptote at y equals 0. Okay, well where on the graph is y equals 0? The x-axis. Yeah, the origin, the x-axis. So what can happen is you can get a graph where you have some type of a vertical asymptote, and then you have a horizontal asymptote here on the x-axis. And what will happen is your graph will do things like this. And you'll get graphs that they're shaped like that. Not necessarily always high in the left side and low on the right side. It could be the other way around, where it's low on the left side and high on the right side. Okay. But if the denominator has a higher degree than the numerator, you got a horizontal asymptote. Okay. When we're doing vertical asymptotes, we've got to be really careful to cancel out any common factors. For example, if you have something like y equals x plus 1 over x squared plus 3x plus 2. We could solve the x squared plus 3x plus 2 equals 0, okay, by factoring it, and it'll factor into x plus 1 times x plus 2. And the way that's set up, it looks like it might be that x equals negative 1 and x equals negative 2 are both troubles. They're both vertical asymptotes. However, what do you notice about that function? Can you simplify anything? Do you see the x plus 1s will cancel? Okay. And if you cancel them, what you wind up with is 1 over x plus 2. In reality, the only vertical asymptote that this function has at x is at x equals negative 2. The only vertical asymptote this has is at x equals negative 2. Notice the other one was canceled in the process of simplifying it or writing it in lowest terms. Everybody good with that? So be careful of that. It's real tempting to go ahead and just factor out the denominator and grab up all of those values and call them vertical asymptotes. But make sure you've got it in lowest terms before you start defining them. Okay. Horizontal asymptotes you're good with? Okay. So here's one. Determine where the horizontal asymptote or asymptotes exist, and the same for the vertical asymptote. Okay, so horizontal asymptotes. Anybody recall where those exist? It's okay to go back and look in your notes. That's why you're taking them. Horizontal. Let's see if the... Oh, wait a minute. They're both the same degree, aren't they? That means that I grab the leading coefficients. 6 over 3 is a fancy way to say 2. So there's a horizontal asymptote at y equals 2. The vertical asymptotes occur where the denominator is 0. So that means we want this 3x plus 3 equal to 0, or 3x is a negative 3, or x is a negative 1. For this particular graph, you would have a horizontal asymptote at 2, a vertical asymptote at negative 1. Make sense? On to number 2. Horizontal asymptotes. Let's see. The higher degree is numerator or denominator? Denominator. So if the higher degree is in the denominator, that means we do have a horizontal asymptote, and that horizontal asymptote is going to be at 0. Second thing to do is to factor out the denominator and see if it'll cancel. Well, that's x minus 2 times x plus 2. Does that cancel? Anything clean up? Nope. So the vertical asymptotes here are going to be at the roots to x minus 2 times x plus 2 equals 0, where x is equal to plus or minus 2. So we wind up with 2 vertical asymptotes and 1 horizontal asymptote. And remember that horizontal asymptote, y equals 0, is on the x-axis. Last case. Tell me about the horizontal asymptotes. Where's the highest degree? Numerator. So that means the function is going to go to infinity. It doesn't have a horizontal asymptote. Does not exist. Is it okay if it doesn't exist? Sure, it doesn't exist. Vertical asymptotes. Take the denominator, set it equal to 0, and we get a vertical asymptote at x equals a negative 1. Okay. So for this one, no horizontal asymptotes. Completely legit. That's fine. Vertical asymptotes, there's 1, and that's at x equals negative 1. Let's take a look at what's going on here. Here's the first one. Recall with the first one that we said that y equals 2 is a horizontal asymptote. That's this line right there. We also looked at the denominator and said, well, gosh, if x is a negative 1, we get 0. That means right there is a vertical asymptote. Now the only thing left to do is to figure out, well gosh, how does the graph fit into that pair of asymptotes? The asymptotes are kind of like fencing. They've set up the field, divided it into pieces, and now the question is, which pieces of the field will the graph wander around in? Well, a pretty easy way to do that is to just pick some numbers that are not an asymptote. For example, x equals -4. If we plug -4 into this, we're going to have 6 times -4 minus 1 over 3 times -4 plus 3. The numerator is going to be a negative value, -24 minus 1. The denominator is going to be a negative value. And even more than that, it's going to be a -25 over a -9, which is 25/9. That's about 3, isn't it? Right around 3 is going to be about there. So if that point's there, do you see that the graph has to be in that field? And it's going to run close to both of the asymptotes, or both of the fences. Okay, so let's move over to the other side. Let's pick something like x equals 1. And see what happens there. Well, we'll have 6 times 1 minus 1 over 3 times 1 plus 3. So that's going to be 5 over 6. Okay, so at x equals 1, it's 5, 6, so it's going to be down pretty low, like right there. So you're going to have a point down there, and you just complete the graph then in that area. Does that make sense on how to do those? It's not too painful. You don't have to get a zillion points. Let the asymptotes guide you most of the way. Okay, let's take a look at the second one. This is the one that had 2 vertical asymptotes, and it has 1 horizontal asymptote. Remember, it has a horizontal asymptote at y equals 0. It can cross the x-axis, but it's going to level in on it as the tails go out to infinity. It has vertical asymptotes where the denominator is 0. Oh, wait a minute. That factors, that's the same thing as x minus 2, x plus 2. So you have 2 vertical asymptotes and a horizontal. Then what you do next is you ask, where does this thing intersect the x-axis? Okay, where is the x-intercept? Well, what that's telling you to look for is where y equals 0. And where y equals 0 is where the denominator is 0. Where the numerator is 0. If the numerator is 0, the fraction is 0. Well, the numerator equals 0 at -1, doesn't it? So we've got a point here. Right there. See it? Okay. So you have a point there. What you can do in that interval between -2 and +2 is to pick some other values out and see what's going on there. Like if x equals 0, we get 1 over -4, don't we? So if x is 0, it's going to be a -1/4. Well, that's about there. If we pick something like -1.5, it's going to give us something up here further. If we pick something like let's say +1.5, it's going to pick something down there, and you get something like that. Notice it crossed the horizontal asymptote, didn't it? Remember, the x-axis is a horizontal asymptote here. Then, far left side. What kind of x values could we pick over there to see what's going on? Yeah, you could use -3, you could use -4, and if you plug in -4, you'll get -4 plus 1 over -4 squared minus 4. So that's going to give us a -3 over 16 minus 4 is 12. That's a -4. So it's going to be a little bit below the x-axis. That must go like that. And you can play the game again over here with +4. And it'll give you above the x-axis. And it'll go like that. So the asymptotes are handy because they guide you as to where the graph is going to go. Okay, so let's take a look at this one. The x squared minus 1 over x plus 1. Well, this will actually factor into x plus 1 times the x minus 1 over the x plus 1. The x plus 1's cancel. This is just x minus 1. Does x minus 1 have any asymptotes? No, it's just a line, isn't it? It's just a line. The domain is fine. It's just a line with a slope of 1, and it crosses through at -1. No horizontal asymptotes, no vertical asymptotes. Is that good? Aha, there it is. Now, one of the things that is useful to keep in mind is notice what they did here at x equals -1. What's so special about x equals -1? Isn't that a 0 there? Yes, sir. Okay. It's not a real point, is it? Because that's a place where it causes the function to be undefined. So that's why they've got the open dot there to say that, hey, this is not a portion of the domain. So you can work all around it. Just works out to be a line. Just can't use that one point. Okay, a third type of asymptote. I usually call them slant asymptotes, but another name for them is oblique. A slant asymptote occurs where the numerator is one more than the denominator in degree. So for example, if you take a look at this, the numerator is degree 2 and the denominator is degree, isn't that a 1 there? Degree 1. So the numerator is in the lead by 1. If the numerator is in the lead by 1, you have a slant asymptote. Now there are two things to notice here. First, we have a slant asymptote. Second, do we have a vertical asymptote? Yes, we do. It's where the denominator is 0. Whoops, that means x equals +1. If you look at the graph over on the right side, you see right there, vertical asymptote where x equals 1. Now, here comes the other part, the sneaky part. With the original rational function, you can do the long division. Yeah, remember that? And when you do the long division, so we're going to have the x minus 1 divides into x squared plus 0x plus 2. Going to do an x, and that'll give us x squared minus x. Subtract this, and that'll give us x plus 2. So this is going to be 1, so that's going to give us x minus 1. And what that's going to give us then is 3. Remainder of 3. So we can, when we do the division, write out what we get along with our remainder. With having a remainder there, that definitely means that we have a vertical asymptote at x equals 1. The first part, where we divide it out, is the slant asymptote. If you graph x plus 1, that's going to give you a line. It has a slope of 1, goes through the y-axis 1 unit above the origin. So what it's going to do is it's going to give us two asymptotes. You see how they're kind of at an angle to one another? And then the only thing left to do is to figure out, okay, we've got 4 separate fields. Which 2 fields is the graph located in? And once again, you could pick some values. For example, I could choose x equals 0. And if I choose x equals 0, that's going to give us 2 over negative 1. Well, if I choose 0, it's down here at negative 2. And right away you can say, hey, look at there, it's down at negative 2. The rest of the graph must be down there as well. And it runs close to the asymptote. For the other portion, you could pick something like, let's pick x equals 2. If you plug in 2, that's going to be 2 squared plus 2 over 2 minus 1. Well, let's see, 2 squared is 4, plus 2 is 6 over 1. So if we're at 2, we're way up here at 6, right about there. And that allows you to say, well, gosh, it's in this field. There it is. A lot of information coming at you today, isn't there? There's a whole lot. All right. Graphing rational functions can get a little on the tricky side. We can start with something real straightforward like 1 over x. The graph of 1 over x, and this is one worth remembering, goes like this. Because the denominator has the higher degree, the x-axis is a horizontal asymptote. Because 0 causes the x value of 0 causes a 0 in the denominator, that means x equals 0 is a vertical asymptote. So you wind up with the x-axis and the y-axis being the asymptotes, which gives you that graph. Make sense to everybody? Okay. And you could find that out by just picking some points and graphing it. Okay. If you do x squared, it's pretty much the same. The only difference is, before, part of the graph was negative, wasn't it? The y values were negative. If you do x squared, can you ever get any negative values out? No. So the one side of the graph is going to go up just like you expected. Then on the left side, instead of it going down, it can't go down because the y values are positive. So you wind up with that side going up and you get what looks like a volcano. Does that make sense? All right, there's not really enough time to go after everything involved with this. So how about we call it quits right there? Yeah, let's call it quits right there. Okay? You can start on the homework on this section because there's not that much left to do here. Okay, there are several sections or several slides, but you've got a whole lot of this done. Folks, congratulations on surviving today. I knew today was going to be a long one. Thank you.
So
Thank you.